Have you ever really stopped to wonder what a decision actually looks like inside a computer? I mean, it's not a person with feelings, right? It's a tiny, brilliant little switch called a logic gate. Today, we're going to pull back the curtain on these fundamental building blocks that power literally everything in our digital lives.
Think about your phone for a second. How does it know what to do when you tap the screen? How does it decide to open an app instead of, sending a text? Well, it's not magic, it's logic. And at the very heart of that logic are millions, heck, billions of microscopic little decision makers. So, let's just get right to it. What even is a logic gate? Well, it's basically a tiny electronic circuit. The best way to think about it is like a bouncer at a club. It looks at the signals coming in, which are either a 0 for off or a 1 for on, and based on a really specific rule, it decides whether to let a single signal out the other side. So, here's our game plan for today. We're going to start with the simple two-letter alphabet that all computers speak. Then we'll meet the three most important rule makers in the whole system. After that, we'll see how you can combine them to create even more powerful gates. Then we'll check out some special gates that can tell if things are the same or different. And finally, we'll see how all these simple little pieces come together to build, well, everything.
All right, first things first. Before we can get into the rules, we need to understand the language they're written in. For computers, that language is binary, just zeros and ones. And the official rulebook for how each gate speaks that language, that's called a truth table.
So what's a truth table? Honestly, just think of it as a cheat sheet. That's it. It lists every single possible combination of inputs a gate could ever get, and then it shows you exactly what the output is going to be for each of those situations. It's the key to understanding how any gate is going to behave. Okay, it's time to meet the big three. These are the absolute most basic gates, the ones that almost all other digital logic is built from. You can think of them like the primary colors of the computing world: OR, AND, and NOT. First up, we've got the OR gate. This one is the most easygoing of the bunch. Its rule is super simple. If input A or input B is on, then the output will be on. It just needs any single one of its inputs to be a 1, and it's happy. And here's what that looks like in the wild. On the left, that's the symbol for an OR gate. See that nice curved line? Now look at its truth table on the right. Notice the only time the output is a 0 is when both inputs are 0. If even one of them is a 1, bam, the output is a 1. Simple as that. Next up, the AND gate. Now this one is way stricter. It's the all or nothing gate. The AND gate will only give you a 1 on the output if input A and input B are both a 1. If even one of them is a 0, you get nothing. Check this out. The symbol on the left has a flat back, kind of like a capital D for AND. And that truth table on the right really shows you how tough it is. There's only one single row where the output is 1, when both A and B are 1. Any other combo, you get a 0. And finally, we have the NOT gate. People also call it the inverter. This one is the simplest of them all, for sure. It has one job and one job only: to flip whatever you give it. You give it a 0, it gives you a 1. You give it a 1, it spits out a 0. That's the whole story. And there it is, a simple triangle with a little bubble on the end. And its truth table is just 2 lines long. 0 goes in, 1 comes out. 1 goes in, 0 comes out. A perfect flip every single time. So now we have our 3 basic building blocks. But here's where things get really, really clever. What happens when we start snapping them together? Well, we can create new, more powerful gates called universal gates. And they're called universal for a pretty amazing reason. You can build any other kind of logic circuit that exists using just one type of these gates. Let's just try a little experiment here. What if we take the output from our friendly OR gate, the one that turns on if any input is on, and we just feed that signal directly into a NOT gate, which we know just flips the signal. You get this, a NOR gate, which, you guessed it, stands for not OR. Its logic is the exact opposite of the OR gate. Now, the output is 1 only when all the inputs are 0. It's like an only if everything is off switch. And notice the symbol. It's just an OR gate with that little bubble from the NOT gate tacked onto again. And of course, we can do the exact same trick with the AND gate. Combine a NOT and an and you get a NAND gate. Its behavior is the complete opposite of the AND gate. It outputs a 0 only in that one specific case where all of its inputs are 1. And here's what that looks like. The symbol is an AND gate with that same little NOT bubble. And the truth table, it's a mirror image of the AND gates.
The output is always 1 unless both inputs are 1. And get this, these NAND gates are so useful, they're called a universal gate because you could actually build an entire computer using nothing but thousands of these things. Pretty wild, right?
So far, our gates have been about pretty simple rules. Any, all, or not. But what if you need to do something a little more complex, like comparing two inputs? For that, we need a special class of gates, the exclusive gates. Their whole job is to see if things are the same or different.
So meet the exclusive OR gate, or XOR for short. Its main gig is to detect a difference. It's constantly asking, are my inputs different from each other? And if the answer is yes, like if one input is a 0 and the other is a 1, then its output is 1. If the inputs are the same, it just stays at 0.
So here's an easy way to think about it. The EXOR gate on the left is our inequality detector. It lights up when things are different. Its counterpart, the EXNON on the right, is basically a coincidence circuit. It only gets excited when the inputs are exactly the same.
And here it is, the exclusive NOR, or XNOR gate. And just like we saw before, it's really just an XOR gate with a NOT gate's bubble attached. Now look at its truth table. The output is 1 when the inputs are both 0 or when they're both 1. It only lights up when the inputs match perfectly.
Okay, we've seen all these individual parts and their simple little rules. But the real magic, the whole point of this entire explainer, is how they all come together to create incredible complexity out of utter simplicity.
Okay, now look at this. Remember our XOR gate, the inequality detector? Well, this diagram shows how you actually build one from the simple gates we started with. We have two NOT gates, two AND gates, and an OR gate, all wired up to perform this one more complex job. This right here is the essence of digital logic. You take simple rules, combine them in clever ways, and you can create incredibly sophisticated behavior.
And that, right there, brings us to our final thought. What we just saw was a circuit made of just 5 simple gates to create a single piece of logic. A modern processor in your phone contains billions of these things. So if this is what 5 gates can build, just try to imagine what billions of them, switching on and off billions of times per second, can accomplish. That's not just logic. That's our entire digital world.